Hi, I'm Sam Kachuck, a postdoc at the University of Michigan working on the Dominoes project. It's great to be here virtually. I'm looking forward to telling you about some of my recent work, but first I want to acknowledge and thank the support I have in performing this work, both institutional and personal. Now, ice is solid, so it fractures, and ice is fluid, so it flows, and the fractures flow with it and extend and join up with other or new fractures, as we see happening in these satellite images of Pine Island Glacier, the neighbor of Thwaites and the Amundsen Sea. We have an intuitive sense that this fractured and crevassed ice in the margins is different somehow from the smoother, more connected ice in the main trunk of the ice stream. But how do these cracks develop? What effect do they have on the flow of the ice? And how can we represent this in our large-scale models? These dynamics are crucial for our projections, say, of Thwaites, where the breakup of the western ice tongue seems to have dragged the eastern ice shelf along their shared margin, contributing to some rifting propagating there. Now, how do we model these? To make projections using a large-scale ice sheet model, we typically start with a given gridded topography, thickness, and temperature product. But throwing these into the equations of motion yields computed velocities that don't match up very well with the observed ones. So, we invert a spatially variable friction field under the grounded ice and a factor to change the ice's viscosity so that, at least at the very first time step, things match up. And we can then integrate the equations of motion forward in time, solving for future thicknesses and velocities as the ice sheet evolves. I want to point out that it's possible that the exponent we're using in the equations of motion isn't the correct one for ice shelves, but we'll continue under the common assumptions for now. With some exceptions, many models assume that things like the topography, temperature, friction, and the viscosity fudge factor stay constant in time. Of course, these things will, in general, evolve with time, and some models are working on incorporating these effects. Temperature diffuses and advects, subglacial hydrology affects the friction at the bed, and glacial isostatic adjustment changes the bedrock topography. But we're going to focus for this talk only on this viscosity multiplier. Here is the inverted viscosity multiplier to get the bicycle's ice sheet model to match observed velocities at 2010. Just to describe some of the features, we see the margins of Pine Island Glacier appear in red, which means they require softening, a lower viscosity, whereas the central trunk shows up as blue, indicating stiffening. These variations in viscosity could be due to a whole suite of effects, including the initial guess at temperature not being quite right, with the main trunk a little bit colder and the margins a little bit warmer or wetter. But this viscosity multiplier might be highlighting other characteristics about the ice as well. See how the softening coincides with the small wavelength roughness on the surface? Though at Thwaites, the correlation is not so evident. Things like ice fabric, cracks, and crevasses, like we saw in the satellite images, could contribute to the inferred differences in viscosity. Rheologically, these might fall under the umbrella term damage, which has come to mean a lot of different things. Some, for instance, define damage as the part of this inferred viscosity multiplier that softens the ice, that is the blue part. Sorry, the red part. So let's take a minute to step back. What we're looking for with damage is some continuum approximation of ice flow in the presence of cracks, so that we don't have to stop and keep track of every individual crack using, say, linear elastic fracture mechanics. It would take too long, and it's not even clear we'd be able to initialize all of those cracks right. Now, a continuum approximation that maintains the average directionality of the cracks would still rely on a complicated tensor that has no clear geometric interpretation. So, we'll leave individual cracks behind and treat nice isotropic fractures, called penny fractures, shown here in a traditional volume element form as Swiss cheese. Although, note that the way damage models traditionally work, the holes of this Swiss cheese would be filled with an inviscid Swiss cheese, like whey, so there's no density contrast between the inviscid and the viscous part. Geometrically, damage is the ratio of the area occupied by the penny fractures to the total area of a face. How do these fractures evolve over the timescale of ice flow? To answer that, we're going to zoom out even further to a kind of vertically averaged crevasse depth, including long wavelength crevasses. Analogous to the Swiss cheese, damage is the ratio of the crevasse height to the total thickness. Now, if we perturb the thickness of ice to thin it a little with a crevasse, the forces would be applied over a smaller area. This increases the apparent stress, which decreases the effective viscosity of the ice, because ice is shear thinning. This drives further thinning, a process that continues until the long wavelength crevasses, or neck, pinches off the thickness, what we might understand as a calving event, or at least a readiness to calve. Via a perturbative approach, Bassis and Ma found that the rate of crevasse growth relative to the thickness of the ice depends on a competition between the hydrostatic or cryostatic pressure tending to force the crevasses closed and the tensile forces pulling them open. Melting of the ice from top and bottom would contribute to this process as well. Using this evolution equation for damage, we can compute an initial steady-state distribution of damage for the Amundsen Sea ice shelves. To generate the steady state, we apply a mass balance that holds the thickness constant, and we don't allow damage to affect the velocity field. The damage we compute highlights those same shear margins and, because of damage's dependence on melt, picks up some of the small-scale features from the observed thicknesses. Although we've taken the initial temperature distribution to make a first guess at the ice viscosity, we haven't used the viscosity multiplier to match the initial velocities to observations. So the only training used here is from the friction field in the grounded ice upstream. Despite that, the damage we compute is very reminiscent of the inverted viscosity multiplier. So let's compare the steady state damage we compute to the inverted viscosity multiplier at each grid point. We're going to focus on Pine Island for now, as this area has the most features that we can compare. There's quite a bit of scatter, but generally there appears to be a negative correlation, where higher damage is associated with lower viscosity. And remember, this steady state damage has so far not used any fitting or training. Some of the scatter could be due to regularization in the inversion for the viscosity multiplier, which makes it smooth compared to our damage evolution equation. Other scatter could be due to temperature variations that we don't include. Also, our damage evolution predicts little to no damage in grounded portions of the ice sheet, so we can't reproduce the viscosity multiplier there just yet. But, taking what we do have, what are the theoretical relationships between damage and viscosity that we should expect? One possibility could be to assume that the effect on large-scale rheology is the same as damage's effect on microscopic rheology, and apply the effective stress model as done in the models of Borstad and Sun, for example. Another member might assume that damage has no effect on the rheology until it really does, i.e. by calving, and the fully damaged ice is immediately made inviscid and removed. This is sometimes referred to as the Nye-Zero stress model. But if we take these as end members, it's possible that anything within this space is admissible. It's possible that small amounts of damage have little to no effect on large-scale rheology. Similarly, ice isn't immediately evacuated, so maybe fully damaged ice doesn't become inviscid immediately. What we want to look for is a monotonically decreasing relationship between damage and the inferred viscosity multiplier. And we're going to allow for an offset to capture any average issues with temperature. Another reason to focus on a single ice shelf for now. We could choose any number of functions, but some high-resolution granular modeling by Astrom and Benz suggests that an exponential function, like the one represented here, captures the transition from diffuse fracture to highly fragmented ice. The vertical offset that we fit at the zero damage intercept translates to a temperature about 3 degrees colder than our input temperature field. And the function suggests that crevasses averaging about a third through the thickness have little impact on the bulk rheology, and that ice that isn't evacuated could still be rheologically important. We'll need to examine the possibility for calving in the future, but at least what we have right here is a way of computing damage, evolving it in real time with the ice, and computing the effect on the viscosity dynamically. I found that the easiest way to compare is through the damage field. So let's see what happens to damage when we allow the ice to flow and impose the melt rate from one of the ISMEP6 experiments. On the left is damage using the static viscosity multiplier, and on the right is the dynamic multiplier linked to the damage field. Take note of how Thwaites' western ice tongue thins and disappears at 2021 with the dynamic multiplier, but takes a little longer with the constant one. and then watch little high damage intrusions develop in the margins of the Pine Island ice shelf and advect forward as the calving funk gains damage and retreats a little bit. The dynamic viscosity multiplier results in faster outflow and thinner ice shelves than with the constant multiplier. But pay particular attention to how the damage in the whole region ends up losing all of its small-scale character and looking significantly different from the damage we showed in the beginning, whether the damage affects the ice's viscosity or not. This is because the ISMEP6 protocol doesn't generate those localized melt rates that we had in our effective melt rate. So if a melt rate is a controlling factor of damage production, then it'll be essential to measure and parameterize for the evolution of the margins and their effective viscosities. To summarize, we've been exploring a forward model of damage that can recreate the commonly used viscosity multiplier with just a few fitted parameters, rather than the million parameters plus a few for regularization of a continuous field. And this model evolves in time. Our preliminary results show promise and highlight the importance of reliable temperature and melt rate measurements, particularly in the margins of the ice shelves, to disambiguate these processes in ice rheology and generate better models of Thwaites' future. But for now, I'll look forward to our discussions. Thank you very much.